We've talked about moment of inertia in previous examples. If we're in space, if we're in XYZ space, then we can find the moment of inertia about any axis. We can take any line in space and any object where we have a density distribution and know the bounds on the region occupied by the object, and we could sum up the mr squared, so that if we consider a typical point at a volume increment, so this is delta V equals delta X, delta Y, delta Z, containing the point Xi star, Yj star, Zk star. Okay, then if we specify our axis, of rotation, and we could also specify just a point of rotation, but let's say we specify the axis of rotation, any line in space, then the contribution of this increment, which we'll call delta I sub small I jk, equals the mass occupying this region, which is our product of our presumed density function, times delta V times Rijk squared, where R sub ijk is the distance of the point xi star, yj star, zk star from the axis. Now I'm going to go ahead and put a star on this R, and then I'm going to specify this is the distance from the axis to the point xi star, yj star, zk star. As an example, consider our sphere, the one we've been talking about for quite some time. Rotating about, you can pick the axis. Let's just have it rotating about the x-axis. For that sphere, the moment of inertia, well, first of all, the distance from the x-axis to our sample point, xi star, yj star, zk star, is what? Well, it's just the square root of yj star squared plus zk star squared. And we can do a quick sketch to verify that if it's not completely obvious. Here's our x-axis, and here's xi star, yj star, and this distance here, this vertical distance, is zk star. How far is it from the x-axis to this point? Well, clearly, since this projection itself projects over to the x-axis at a right angle, this segment, which should be straighter than I drew it, is the hypotenuse of the right triangle. Here, and that right triangle pretty clearly has legs yj star and zk star, so that its hypotenuse is our distance rijk star equals the square root of yj star squared plus zk star squared. So that brief picture demonstrates why this is the distance. So that what we have to integrate is we have to integrate mr squared. For a typical volume increment, and what do I mean by the volume increment? I mean this volume increment, a delta V equals delta x, delta y, delta z, containing our sample point. Then mr squared equals our density at xi star, yj star, zk star, times delta V times, didn't leave myself room. Okay, I just did kind of a quick patch. I'm going to have to multiply. Times the distance from the x-axis to the point being the square root of xi star squared plus yj star squared, that quantity squared, which equals then, leave myself enough room this time, delta of xi star yj star zk star, and I'll leave my delta V off until the end. The square root of this expression is just times xi star squared plus sorry, it's getting late. I can't really see this from where I'm standing. This is yj star plus zk star, yj star squared plus zk star squared. So I've corrected this one, and let me quickly try to prepare this one. So that's going to be the square root of yj star squared plus zk star squared, and that quantity squared. Okay, so when we get down to this expression, the square of this expression is going to be just yj star squared plus zk star squared, and then our delta V, we have room to write this out if we're careful, delta x, delta y, delta z. Now this expression approaches an integral, and I'm not going to try to squeeze that on, try to use better judgment than usual. But this expression in the limit approaches the integral of delta